Welcome to our new series on dynamic discrete choice models. Up until now, we've discussed at length different versions of the logit model, be it generalized extreme value or basic logit or mixed logit. And now we're going to introduce a dynamic dimension, which just means that today's decision depends on expectations of what might happen in the future. Dynamic decisions fundamentally incorporate an intertemporal trade-off, acting now versus waiting for potentially better options later. Examples include job search. Should I take the job offer that's given to me right now or wait for a better one? Or replacement and maintenance of equipment. And in this video, we'll introduce the notion of optimal stopping, which is a mathematical framework that captures this timing dimension or intertemporal trade-off. It turns out that a lot of important problems in economics and finance can be boiled down to the question of when to optimally stop. Let's introduce some basic concepts in the following slides. Let's talk a little bit more about optimal stopping before we get into further details. Optimal stopping is a mathematical context for either maximizing rewards or minimizing costs. And optimal stopping problems are by definition dynamic, and many economic problems involve optimal stopping. The canonical one is the secretary problem, which is a question of how many candidates should I interview before I'm confident that I've got the best one in the pool and should offer that one the job. There's also many applications of search theory more generally. Employees could be searching for a job. People could be searching for a spouse in the dating market. People could be searching for houses to live in on the housing market. These are all dynamic problems where people are considering what's happening now versus what could happen in the future if they waited a little longer. There's also a lot of problems in finance that can be boiled down to buy or sell or hold. And there's also problems of infrastructure maintenance where we want to consider when should we replace this machine or when should we make the repairs on our house. Because these assets are not perishable, they're durable, then that makes it a dynamic problem. And most optimal stopping problems inherently have a tension between costs and benefits. It's costly to interview more job candidates, but it's also costly to miss out on the best candidate. And in terms of how we actually mathematically solve models that have optimal stopping, we use something called dynamic programming in a discrete choice setting. And we'll get into this in future videos in this unit. And there's different ways that we can think about this discrete choice setting unfolding. So in one case, time could be discrete, or in another case, it could be continuous. And if we have continuous time, then we're going to use a certain set of tools called Hamiltonians and differential equations. If time is discrete, then we're going to use methods called recursive methods. And independent of whether time is discrete or continuous, we also have to consider the time horizon. And what this means is, are the decision makers finitely lived or are they infinitely lived? If time horizon is finite, then we can use dynamic programming combined with these recursive methods. If the time horizon is infinite, then we need to use dynamic programming, but also solve for a fixed point. And we'll talk a little bit about that in a later video in this series. So we can consider these four different combinations that are all viable solution methods for discrete choice problems. So we can have any combination of continuous time, discrete time, and finite horizon and infinite horizon. And we're going to use, if it's continuous time, Hamiltonians and differential equations, and we can solve that by something called finite differences. But then in either case, if we move to infinite time horizon, then we also need to solve for a fixed point. In this mini-series, we're going to mainly focus on discrete time and finite horizon. We will talk a little bit about discrete time, infinite horizon later, but that is the main idea for what's to come in this mini-series. So hopefully that gives you a little bit of an intuition for what the main idea is behind dynamic discrete choice models and when they can be useful. Up next, we'll add a little more mathematical formality to these ideas. And in particular, we'll introduce some of the mechanics for solving these finite horizon discrete time backwards recursion problems. So I hope to see you in the next video.